So, this is Mr. Yeager, first off. And again, we are finishing up projectile type problems. This time we are looking at the angle launches. So again, we've gone through all the concepts with the different, with what's involved with projectile launches. What is a projectile? And we looked at the 0 degree launches, but what if now that you launch this at an angle? So that's what we're going to look at now. Okay? So here we go. So with angled launches, there's going to be a bit more you might have to find. Obviously, there's not, I mean, when we practice problems, they're going to have to find everything on a test. They're going to ask you, obviously, pick out one thing or another thing to try to calculate. And on the AP test, it is much more likely that they're not going to actually make you calculate anything. You just got to be able to put it into symbol form. So I'll try to show both as much as possible, again, because this is for both AP and regular physics that you'll be doing this. I mean, I'm hoping the idea is if you can do the math, you know what symbols are being involved in the formula, and so on an AP test, you don't worry about the numbers, you just write out the equation that you would use. That's basically what I mean by symbols. Okay? So, one of the first things really just to understand is for angled launches, we are going to make up positive and down negative. Okay? That'll just make everything so much easier to try to do. Even if the object only goes down, when you have an angled launch, it will be easier just to say up positive, down negative. So any of the quantities, displacement, velocity, or time, that is up or down, make it appropriately that way. So you'll see here, if you shoot something upward, we're going to say the initial y velocity is positive. If you're shooting downward, the initial y velocity is negative. Okay? All right. So really, like I mean, because we basically know everything already in terms of what we should use, we need to just jump right into a problem. So we have this cannonball is shot at a 30-degree angle above the horizontal at 20 meters per second. So the first question is, how long will the cannonball be in the air? So again, this is about time, and whenever we solve for time, unless things are so much given to us, which they usually are not, we're going to use the delta y equation. We use the y to figure out how long something stays in the air, because it's going to be the acceleration due to gravity that will determine how long that object is able to stay in the air. Okay? So this object is shot off with a velocity of 20 meters per second. That's the angled velocity. That velocity will not be used in any formulas that we are interested in because it's not going to help us. It's going to be changing constantly throughout the flight, so that's not what we're going to be using. Just so we remember, just for good conceptual practice, at the very top of the flight, the object only has a horizontal velocity. Y velocity at this time is 0 meters per second, but the object is being accelerated at that point. It is being told to change directions. When you change directions, you accelerate. So gravity, again, is always pulling it down. Okay? I'll go ahead and mention this too, even though it might show up again later. This flight will be symmetric. Okay, the flight is symmetric. All right, which means any point on the opposite side of the arc, everything will be equal to each other. Everything magnitude-wise will be equal to each other. The only thing that'll switch is, I'm going to make this up. At this point, maybe the y velocity is only 2 meters per second. Well, it would be positive 2 meters per second. Over on this side, it would be negative 2 meters per second, the y velocity. Okay? But it is a symmetrical flight through the whole thing. So the time that it takes to go up in the air, right here, this would be time 1/2 over the entire time that it's in the air for. Okay? So that's just something to keep in mind as well. We'll use that probably in some of our calculations. Okay. So, again, you're given the initial y, the initial velocity. We want to immediately change this into x and y velocities. Okay? Like I just said, and the biggest mistake, one of the biggest mistakes I see people use is they'll plug that 20 meters per second into a problem. Once I see that, I know this person doesn't know what they're doing. It's all wrong. Let's move on. Okay? I like to spend some time in the problem. So unfortunately, when I see that, that's a quick problem just to say, well, nothing's going to be correct in this. All right, so a cannonball is shot at 30-degree angle above the horizontal. Well, we already saw that, sorry. So finding Vx and finding Vy, sorry. This is why we did our vector math, all right? We have to be able to quickly do this. This is something that we're not sitting there going, what am I doing? What am I doing? What am I doing? we should be getting to the point of going over time, obviously over a day or so, of saying, okay, change that into x and y. Remember, if I draw out my triangle, you see down here, okay, the angled velocity, that is your resultant velocity. Draw out the component vectors, okay? I have a horizontal and a vertical component, all right? If I draw it this way, it will always be, the x component will always be v cosine theta. So again, for those in AP, the horizontal velocity is v cosine theta. The vy velocity, v sine theta, okay? So again, we should be able to calculate both of those out fairly quickly, okay? So we get both of those. Now I have my x and y velocities. Moving on. All right. So I wrote it out as initial x and initial y because they're the components. But one thing we want to say right away, the horizontal velocity never changes. So a lot of times I just get rid of the little I and say it's my vx velocity because the horizontal velocity never changes. Only the vertical velocity will change. Okay? Going back to that one diagram where I was showing you the symmetry of it, there really is no symmetry in the horizontal direction. It just stays the same the entire time. All right? Everywhere it is Vx. That's again how you can find the velocity at the top of the flight very quickly. It'll equal V cosine theta Vx because that's the only type of velocity it has at the top of the flight. Okay? But the vertical velocity will decrease as it goes up and will increase as it falls back down. All right, so we're going to get to this answer eventually. Now that we know Vx and V naught y, you can see I don't just label it Vy because the Vy does change. We can now solve for time. We have two possible equations. Dx equals Vxt. This again won't work because you only know what Vx is. I don't know the range, so I can't solve for t. We do not use the x formula to solve this. We go to the delta dy, the change in the vertical equation. Now for this one, it's different from the zero launch because I now do have an initial y velocity. This is the formula we're going to use. Okay? Now people sit there and go, oh, that sounds like that's going to be really tough. Okay? Well, we actually do know 3 out of 5 kinematic variables. We know the initial y velocity, we know g, and this is where some people go, wait, we're solving for t, how do I know delta y? Well, we're looking for how long this object is in the air for. Think about where it starts and where it ends. What height do you begin with and what height do you end with? Okay? Well, it turns out, okay, sorry. Let me go back. We do have, again, V naught y and g. I want to make sure it's clear. G is going to be negative in this because the initial y velocity you've made is upwards. The initial y velocity is going up. And so if you write, which most people do, they'll write this as 10 meters per second. That means up is positive, down is negative, like I said before. So g is always downward, it's going to be negative. So we have those two values. Sorry, I jumped the gun on delta y. So we're solving for t, which means you must know delta y. Why? Okay. All right. This is what I was getting to. The delta y is going to be equal to 0 because where do we start? How far off the ground are we at the beginning? Y initial equals 0. At the end, we're going to be back on the ground. Y final equals 0. So your change in height during the whole flight is actually 0. I mean, that's a very nice little thing to notice here. Again, we're not going to say the final velocity is 0. Don't tell me the final velocity is 0 because the idea is this is right as it leaves the ground and right as it hits the ground. Okay, what is occurring? And so the delta y is actually 0, which makes this problem immediately a lot easier to calculate. Okay, you can go and calculate it now. All right, we can now solve. 0 equals 10t plus 1/2 negative 9.8t squared. Again, we're going to use 10 a lot. This would be a lot easier if I used 10, but we'll leave it as it is. So this will equal 10t minus 4.9t squared. So 0 equals 10t minus 4.9t squared. I just combined the 1/2 and negative 9.8. I add the 4.9 to the other side. I'm going to do this very slowly so everybody sees it clearly. Add 4.9t squared to the other side. So So now I have 4.9 t squared equals 10t. I can cancel out one of the t's because they're on both sides. So I'm left with 4.9t equals 10, t equals 2 seconds. T equals 2 seconds. Okay? Basically, obviously with a little bit of rounding there. So again, where am I getting out of this? We know the initial y velocity after we resolve the vector, after we change it into x and y. We know g is negative because the acceleration is always pointing downward, but the object initially starts moving upward. Delta y is going to be 0 because it starts and ends in the same position. Okay? Obviously, the problem gets a lot more difficult if we're not starting and ending at basically not a change. When we do problems where somebody plays catch with somebody else, we're going to say basically both people are catching the ball at the same height. Okay? They catch it at the same height. They throw and catch it at the same height. So we're going to try to keep that because if not, the problems get a lot harder, which we're going to see at the very end. Okay? So the cannonball is in the air for 2 seconds. So the next question would be, how far does the cannonball travel? Once again, this is an easy part. We're looking for dx. The only equation is dx equals vxt. I know what vx is. I know what t is. I solve. 17.3 times 2 is 34.6. So that's how far this person went all the way across, or this object went. It was only in the air for 2 seconds, but it was able to travel 34.6 meters in that time. All right, the next question. All right, what is the maximum height the cannonball reaches? What we're looking for here is what is the height of the highest point of the trajectory? This height right here, like it has drawn. Okay, so we want the highest point of the trajectory. Okay, when will this occur? Okay, so this is some of the stuff I already talked about. Do you notice anything about the trajectory? It is symmetric. So again, it's going to occur at halfway point during the total flight. So therefore, it's going to reach the top height at 1 second. So we know t, we know y, we know t, we're solving for delta y, we know g, so we have enough variables. Okay? Again, since this is asking for delta y, we have to go with a y equation. Okay? So what do? You're going to use the delta y formula again. We're doing a completely separate problem. We're not looking at the whole trip. We're only looking at a partial point of the trip, so we can use the same equation again. So this one, I just need to plug everything in. All right? Delta dy max is v naught y plus 1/2 gt squared. I have all my variables. I plug it all in. 10 times 1 plus 1/2 times negative 9.8 times 1 squared. 10 minus 4.9. It'll reach a height of 5.1 meters at that point in time. Okay? There's actually a second way to solve this problem in one step, and that you don't need time. Okay, I want to show this to you just in case, because maybe it's asking this question, and I give you all the information. There's actually a one-step way to do it instead of dealing with time. Obviously, time can work, but watch this. Okay, what is the Vy at the top of the flight? What would be the y velocity at the top of the flight? We all know Vy at the top of the flight is 0. So therefore, I can go to a different equation. I know the final velocity in the y direction is 0. The initial velocity that it shoots out is 10, and I have g is negative 9.8. So guess what? I do have 3 out of 5 variables. I just need to find the appropriate equation that uses all these variables and has delta y in it, and that's what I have right here. If you solve, it's going to come out to 5.1 as well. Okay? So that's just a second. There's multiple ways to solve the problem. You choose how you want to approach it. All right? And obviously, what would be the fastest way to go about it. Okay? So a couple things for angled launches. Okay? This is not just for any type of launch. The horizontal velocity is constant. The vertical velocity is accelerated by g. Okay? The flight is symmetric if you start and end at the same point. Again, over 90% of the problems are done that way. All right? There's obviously ones you can find in a textbook that don't. They're going to involve a bit more math. They're going to be a little bit more difficult to maybe do. Okay? This means the object will reach a maximum height at the halfway point. Okay? The vertical velocity at this point is equal to 0. Oh, sorry, I'm reading that wrong. But the vertical velocity at the very top is equal to 0. But it also means the magnitude of the vertical velocity is equal on both sides of the trajectory, which we talked about before. Gravity always points down. All right. well, there you go. Vertical velocity is 0 at the top. All right, so I bring this slide back from our introductory video. All right, again, we can see this is a symmetric flight. Horizontal velocity stays the same all the way throughout the flight, including at the top. The speeds on opposite sides, all right, are equal, but the velocities are opposite to each other. And again, acceleration due to gravity would be down the entire time, 9.8 meters per second squared or 10 meters per second squared. Now, there is a challenge problem. This is something that is done in regular physics, actually more than AP physics, okay? But who knows if it happens to show up on AP for some reason too. If a person throws a water balloon at 5 meters per second at an angle of 45 degrees below the horizontal, and the person is on a 10-meter high building, how long will it take for the water balloon to hit the ground? Okay? For this one, the reason this is not an AP problem is because we don't use the quadratic equation. That is something in the AP committee book, basically saying you only need to be able to do simple algebra. I don't think quadratic equation is that difficult, but if you're going into a quadratic equation, you're probably doing something wrong. And the thing is, this problem requires you to have to use the quadratic equation. In regular physics, you will get problems like this. I do like to give this type of problem because it does show your ability to obviously handle a slightly higher level problem. So, the answer is 1.1 seconds. So let's see how this is done. I'll go ahead and show you how we go through this. Okay. So, you shoot an object straight down. I believe it says we're 10 meters high. Not 10 meters, just 10 meters high. Let me make sure. Okay, 10 meters high, 5 meters per second. Okay, good. All right. You are 10 meters up. You're throwing a water balloon down at 5 meters per second at 45 degrees below the horizontal. So I draw in my x and y components. Okay. And this one's just asking for time. I'll probably add in the distance that it goes to just so you can see that. But it's asking for time. How long is this object going to be in the air for? Time depends on y. So I'm going to do delta y equals v naught yt plus 1/2 gt squared. Okay? 1/2 gt squared. The thing is, this 5 is not the v naught y. I need to find v naught y. So 5 times sine of 45. 5 times sine of 45. I need my calculator here real quick. Okay. And that will equal 3.5 meters per second. Now the thing is, this is one of my rules with these, as for angle launches, I just think it's going to make your life a lot easier if we say everything down is negative. Now you might sit there and go, wait a minute, it's only going one direction, why can't I make everything positive? You can. You absolutely can. I'm just going to make it negative though, because that's going to help our quadratic equation in the end. I know what's going to happen, obviously. Okay? So this is actually going to be negative 3.5 meters per second. The distance, I'm going to lose 10 meters. So my delta y, this is v naught y, my delta y is equal to negative 10, and g will equal negative 9. I'm going to actually use 10. Negative 10 meters per second squared. Okay? So if I plug this into my equation, I'm going to go to a new slide. I get negative, I'll write it out, delta y equals v naught yt plus 1/2 gt squared. I get negative 10 equals negative 5t minus, well, plus, I'll leave it that way for now. We'll do every step. Plus 1/2 times negative 10t squared. The thing is, I'm going to multiply 1/2 and negative 10 out, and that's negative 5. So negative 10 equals negative 5t minus 5t squared. All right, so what you can see here is you go, oh no, I got a quadratic equation. And nothing is 0, so I can't just simply cancel everything out and have an easy problem, just like all other projectile problems. So I want to write this out as an official quadratic equation. When I write an official quadratic equation, I have it equal to 0. So in other words, I'm going to move both of these things to the other side. How do I do that? I add them to the other side. So I'm left with 5t squared plus 5t minus 10 equals 0. Now some people will go, well, I'll start trying to factor. Don't waste your time. Go ahead and just plug it straight into the quadratic equation. So that is, remember, this is A, B, C. I'm not even going to write it out because you should know this by now. Negative 5 plus or minus the square root of 5 squared minus 4 times 5 times negative 10. negative 10c, all over 2 times 5. All right? If you plug this all in, let me go ahead and confirm. All right, sorry, double checking something. Oh, I'm being stupid. I already realized my mistake already. The v naught y was not 5. Whoops, whoops, whoops. Sorry. Woo! I'm doing this and getting a wrong answer. That's not the 1.1. All right, so let's try again. Sorry. This will be negative 10 equals. This is negative 3.5. That's what it was. Ugh. Such a silly mistake. So negative 3.5. All right, this is going to go a lot faster now. T. All right, minus 4.9t. Sorry. 5t squared. Here we go. 5t squared plus 3.5 minus 10 equals 0. So I'm going to do now negative 3.5 plus or minus the square root of 3.5 squared minus 4 times 5 times negative 10 divided by 2 times 5. Now let's do this, and it'll come out all nice for me now. Yep. That's so much better. All right. So essentially, the only thing I'll quickly say, it does come out to 1.1 seconds. What you're going to realize is, obviously, we usually get 2 answers. The thing is, again, and this is all solving for time. The thing is, the square root has to come out to a positive number. I mean, you got to. If it doesn't, obviously, you're going to get an imaginary number, and that's not what we want. So that has to come out to a positive number. Since I have a negative number out front here, if I do negative 3.5 minus this, obviously I'm going to get a negative answer, and we can't have such a thing as negative time. So the negative time answer, we just completely discard and don't do. So basically what I did is I solved for the square root. I added negative 3.5. I still have a positive number. I divide that by 10, and I get 1.1 seconds. Okay? So, again, okay, I practiced this with both regular and AP. AP, we will not have this on the actual test. Regular, we could. All right? So maybe you feel like that, oh, should have taken AP. Should have. All right? But, you know, this is just another example. This is the only situation when you're shooting downwards from a height, okay, or throwing something downwards from a height, that we would run into the quadratic equation. Other ones would be where, like, you want to throw something over a wall or something like that, but we don't do those problems too much. You know, we try to have it where something cancels out, something is set to 0, and we can solve fairly easily. All right, so that's it. That is projectile motion. Thank you.